first two, all you had to do was, like the direction said, just find the mean and the standard deviation for the sample. So we determined that the mean for the population is the same as the mean for the sample. That is a given, so no changes to that. The only thing you have to change is the standard deviation. It's going to get divided by the square root of n. And the difference between these two is nice because this took a 50 and this did a 250, with all other information being the same. So therefore we confirm that as the sample size gets larger, your sample standard deviation will get smaller. Okay? A little bit more exact, if you will. Okay? So we determined as the size of the sample increases, not the mean of the sample increases. Nope, the mean stays the same. The mean will stay the same. And the standard deviation will decrease. So that one had a double whammy in there if you went that one. A sampling distribution is normal only when the population is normal. If that is one case, but if the sample size is greater than or equal to 30, that is the second case. So that had to be a false. The graphs for number 9, so what they were looking for is this. This is the waiting time in seconds at a traffic light. And this is your relative frequency. This has happened for a long time. But does this look like a normal curve? No. So now I'm going to sample 100. I'm going to take a sample of 100. Because my sample size is greater than or equal to 30, my sample curve will be a normal curve. That's one of my conditions. Either the population is a normal curve, and it's automatically, or the sample size is greater than or equal to 30, which is in this case, because my sample size is 100. Now, your mean has to stay the same. So look at all your means. Well, here's your mean. Sorry. Where's your mean? Here's your means. Look at all your means. Your means have to stay the same. This guy changed. So it can't be that one. Agree? Means have to stay the same. Your standard deviation has to say standard deviation divided by the square root of n. Your standard deviation is 11.9 divided by the square root of 100, which is 10. So it just moves this decimal point over 1. So it can't be this guy. They didn't adjust the standard deviation, but this one they did. So there's your curve. It's a narrow little curve, as opposed to like a wider curve. Look how small your standard deviation is. The means have to stay the same. That's the rule for central limit theorem. The mean stays the same, but the standard deviation changes. So this one, you basically just had to draw a sketch for me and find your new standard deviation. I didn't draw the sketch, so hopefully you guys did. What this shows you too is that your mean is going to stay consistent through all three of these. The mean stays the same throughout everything. My mean stays the same. Here's my sample. My mean is the same. My standard deviation is going to change based on n. So the first problem, I take that and I divide it by the square root of 12. My standard deviation has shrunk. So technically, I missed. I started out with a curve that looked like this. Here's my mean in the middle, 154, and I went out 5 each time. So this is approximately like 159 something, 164 something, just kind of approximate. Now I shrunk my mean down to 1.4. So now I'm going within here, I'm doing 3 of these. My curve is getting narrower. My curve is going to go up like this. This is going to shrink it down even more. My curve, if possible, is getting even narrower. This guy is shrinking it down even more. So now my curve is getting even narrower. in here, within that space. So again, we could see, and these were good ones to look at, because as the n gets larger, it makes sense. You're dividing by a larger number, so you get a smaller number. Your standard deviation gets smaller. Okay? Makes sense? Now we get to the good stuff. For some reason, I think it's because this is zoomed in. Let's see if I can zoom it in. Oh, better. Hello, did you have this? Hold on. Sorry, did you have this? Yeah. You weren't here yesterday. Okay. This is the work you had for yesterday. Got it off? Why? So you're supposed to finish this for homework. All right. So for those of you that didn't do it but claimed you didn't know how, make sure you're writing this down. The mean salary for an environmental compliance specialist is about $66,000. What is that? Where did that come from? A sample or a population? What kind of statement is that? Is that a statement about a population or a sample? A population. How do I know that? Because they didn't say from sample of. They made a random statement. So this is the same as saying for all environmental compliance specialists. This is a statement about a population. Now they're telling me something about my sample. I random sample 35 specialists from this population. Ah, that confirms that was a population of all my specialists. What is the probability that the mean salary, because don't forget, I keep doing these and I take the mean of all the sample means, not just one X, that's the mean salary of the sample, is less than 60,000. So technically, this should be my probability statement. My sample means from my samples is less than 60,000. Now, our sketch is going to pertain to our sample, because we don't want to sketch the population, then find a sample and sketch it on that. It is a mess, because you're like making a little tiny little piece in the middle of nowhere. So we're sketching our sample, and it is exaggerated, just as we do the other ones. So we need to know that your mean stays exactly the same, but that your standard deviation is going to change. So n, I put in here, this is my formula. I divide 12,000 by the square root of 35, and I get approximately 2028, approximately there. So that's where I'm going to make my curve from. This curve is for my sample. Even that's pretty high, right? Okay, so they told us to assume that the population standard deviation was 12,000. So now, I look at my 60,000. It is less than 66. So I kind of just went more to the left than to the right. So 60,000 comes probably somewhere over here. And I want less than to the left. It's a little piece of my curve, isn't it? I expect a little percentage. So I use my formula. My formula has changed. My old formula said x minus the mean over the standard deviation. So we changed it to say, take your sample means and divide this guy by the square root of n. That is the only thing that you're going to see different. That x value is still an x value regardless if it was a sample mean or just an x. So I plug that in there, and I plug it into here. You can use your calculator. Be careful if you don't have one with the software that you put parentheses around here. parentheses around here. You get a z-score of negative 2.96, which we expected that to be really, really low out there. We look up our area to the left, and our area to the left is 0.0015, which means there's less than 1% chance from all my sample means that I'm going to get a salary less than $60,000. Because I tightened up the field. I made it closer to the mean. I made it closer. But what the funny part is, if I look at it on this side, I get much more percentage. And we'll look at some of the greater thans. So, if anybody didn't have this, did you write this down? You have to know how to do this. If you did this one, you can do every one. They're all the same. Questions? Nope. Okay. All right. 29. During a certain week, the mean price of gasoline in the New England region was $3.79.796. Gasoline always goes out 3 decimal points for some odd reason. It's usually like 99. So if they tell you it's 2.999, it's really $3 that you pay. They just like to make it look like, oh, you're not paying $3 yet. So they always go out 3 decimal points. This is the population average for this whole region. Just the population of the New England region. Now, I can't still reach every gas station in my New England region. So I sample 32 of these gas stations at a time from this population. So that again tells us it's a population. What is the probability that the mean price for the sample was between $3.781 and $3.811 that week? Assume the population standard deviation, and they have to give me this because I need this, was 0.045. Not a lot of variance between them. So I sketch my graph. My mean is the same. Somehow my numbers kind of slid on top of each other here. My mean is exactly the same. I'm still 3.796. There's my mean. I'm an in-between, so I take my standard deviation, I divide it by my 32, and it's very, very close to this. So set your graph. Look how close you are to the middle. So close to the middle. You don't have a lot of distance between 3.712 and 3.82. That's how small, how tight that is in that curve. So again, an in-between says take the value per x, each one, these are really my sample means, take the value for your sample means, find the z-score, find the z-score for the other one, find their areas, and subtract their areas, not their z-scores. And you will get the answer. Now, this is a great one to put in your calculator. The in-between have a lot of work. So, if anything else, get used to doing this one. We're on a normal curve. We're accumulating all our area. You don't have to worry about your limits this time. I know some of you panic over where that limit is. But you have your endpoint. 3.781 and 3.811. You have to change the mean to reflect your mean, which was 3.796. Now your standard deviation changed. So let your calculator do your standard deviation. 0.045 divided by the square root of 32. Just be careful because in this, it gives you a parentheses for your square root. You just have to close it. So it's telling you, I want this number under my square root sign. Just make sure you close it. Now paste. There's my answer that I got before. And it's rounded to 4 decimal places. 0.9407. So is it close to this? Pretty darn close. Your calculator is far more exact because we rounded this Z-score and this Z-score. We took the areas out of the table, which only goes 4 decimals. Yes. So you're going to bypass all of this. You're going to bypass this. You're going to bypass this. You're going to give me a sketch. You listening, Sarah? You're going to give me a sketch. You're going to give me this and this and this. And you're going to say calc. And if this is a test, I would write down the things that you put in your calculator. Because here's the problem. If you enter something wrong, I don't see it, you don't see it now. And I can't give you any credit for that work. But I mean, I know what a calculator, I do it on the calculator as well, so I know what the calculator should give me. If you gave me 0.9499, I would say it's wrong. I don't know where your answer came from. But if you showed me and then say maybe by accident you divided by this, maybe you did this part, and you said, oh, divide by the square root of 36, then I would say, oh, you just put it in wrong. And most of the times I just correct it, and I don't take any points off for that kind of stuff. But the worst part about the calculator is you don't see it after it's done, because you moved on to the next problem, and I don't see it. So therefore it's hard to give partial credit. So if you're going to use your calculator, and I love the calculator on the in-betweens, a lot of you struggle with the, what do I do when my lower limit, what do I do with my upper limit? Well, those are your 2 limits. And it makes it nice. And you bypass this whole thing in here and give me one answer. So show me what you put in your calculator. Just 4 little things that you put in your calculator. Okay, so there's a 94% chance approximately that my sample mean price is between, the probability that my sample mean price, if I pull out a sample, it will be between those 2 numbers. And they're pretty close to begin with, because look at how close their population standard deviation was. Within like 5 cents of each other. 5 cents is not a big difference. Usually you see a lot more variance in your gas prices. Usually it's a bigger difference. I know my daughter and I just we had to go to Ellenville for my stepdaughter's wedding party thing, but the gas up there was 20 cents cheaper than the gas in New Windsor. 20 cents. That's a big difference.
Gas in New Windsor, someplace pretty cheap too.
I go because I live right by those gas stations over there. I live by there. I always go there. That's the cheapest one.
The gas in Hoover.
Yeah, by far. Cumberland and New Windsor used to
Yeah, that's
be cheap too.
ridiculously cheap. It's like 27 cents less than a quick check on my house in Hoover.
But Ellenville is 20 cents cheaper than our gas. Because my son told my daughter, can you take my car home because I'm going to get a ride from football games that he had to go to? So my daughter's like, Mom, don't leave without me because I don't have my wallet. I'm sure my friend sure he doesn't have gas. Damn if he didn't have gas in his car. So 20 cents cheaper. That's a big difference. Okay, so let's move on to the next one. You guys should be able to do these. Okay, the mean height of women in the U.S., the mean height, it should be height, of women in the U.S. is 64.2 inches. Is that a population statement or is that a sample statement? And what tells you that? And what does it say? Of women in the U.S. So, do we have more people in the U.S. than women in the U.S.? That's our population. And it kind of gives it to you in the next statement, probably. So that's a population statement. It also tells me down here, assume my population standard deviation is 2.9. So basically, this is the only information that I need to pull out of there about my population. So then I read, a random sample of 60 women in this age group is selected. What is the probability that the mean height for the sample is greater than, and again, it should be an X bar, is greater than 66 inches? Okay, so now, I go to my chart, I have to place this, I have to sketch, you have to give me a sketch, but I want a sample sketch. So I need to know that my N is 60. That is the only new piece of information. So how do I know I'm using the N? Because they gave it to me. If they didn't give me an N, I'm picking one person out of the population. But I'm picking a sample, a random sample to test it against all the sample means that I found. The average of the sample means. So I find my new standard deviation. Look how small that is. The standard deviation before was fairly small, 2.9. But now look how small it is, far less than half an inch difference. So I label my chart. I find where 66 is, approximately over here, and I want what percent is greater than this. So greater, remember, to the right, it's going to be a very small number. When I look this number up to the left, isn't it going to be close to 100, probably? I look up the large number, and then I find subtract from 1. So I do this, I come out with the z-score that is not on my table. The highest z-score on your table is 3.49. Agree? When you look up 3.49, what is the area of 3.49? 0.9999 something, right? It's probably got all 0.999. But this is the area to the left. I got to do the 1 minus this guy. So this is approximately 0 because I'm a little bit further up than that. It's approximately 0. And let me confirm it this way. If you guys are comfortable with your calculator again, I'm going to go to inverse. I'm going to go here, and I'm going to say my lower limit, I'm just going to use my z-score, is 0.481. My upper limit, no, 999, that's fine. I'm going to set this back to 0 and set this back for 1, just because I want an area. Your calculator can find your area. Even though your table can't, your calculator can. Look at this guy. I never have a probability greater than 1, do I? So what does this guy mean over here? 7 positions to the left. Look how close, like I'm just approximately 0. I would have 0.6 zeros and a 7. Approximately 0. Okay? Your table only goes up to 3.49. So anything to the right of that is approximately 0. Anything to the left of that is approximately 100. Not exactly, because there's no exact number on this, but approximately. If you're okay with this one, it always throws kids off when they get a higher z-score. And you can get a z-score of 1,000. That can happen. Okay. Okay. 33. Assume the heights in 31 are normally distributed. Okay. Are you more likely, and this is a very, very good question. If any other question, make sure you understand this one. Are you more likely to select one woman with a height less than 70 inches from, I'm only selecting one woman. This comes from my population because it doesn't say select a sample. Or are you more likely to select a sample of 20 with a mean height less than 70? So I'm again, just like example 6, I'm comparing my population to my sample. So my population says X is less than 70. I didn't do the sketch for both of these, but maybe I probably should have. Plug in your formula. No divide by n because I'm dealing with one person, one random person from my population. So I subtract my x minus my mean, divide by my standard deviation. I find my z-score. Here's my z-score of 2. I want it to the left, and I look up my area. It's close to a 98% probability that I will pull out, select a woman whose height is less than 70 inches. It makes sense, doesn't it? Makes sense. If my average was what? 64.2? Yeah, it makes sense that a large of my individuals will be less than this. Because 50% is less than 64.2. Now, my sample says you have the same mean. However, you're going to have to change your standard deviation. You're going to have to tighten this up a little bit. So I'm going to take my standard deviation and I'm going to divide it by the square root of 20. I don't think I did. Oh yeah, I did it over here. So you could see that it's less than 1. It went from 2.9 to less than 1. So now look at my z-score. My z-score is way out over here somewhere. The area to the left now is approximately 100. To select this sample, pretty much you're right on target. You have almost 100% probability that you will select a sample who is less than 70 from your sample. So I had a far better chance of selecting my sample. Do you see what it does on the right-hand side? On the left-hand side, it made it a lot smaller because your curve, bigger your curve, has little pieces on the end, right? But from the right-hand side, you're using most of your curve now. So hopefully you get that one, right? All right, number 36. A machine is set to fill milk containers. This is one of the reasons why we use these things. With a mean of 64 ounces and a standard deviation of 0.11 ounces. Population statement. It didn't say it came from a sample. I'm filling all my milk containers from wherever this is for 64 ounces and a standard deviation of 0.11. You have to have some kind of cutoff because, granted, you're doing this by machine. Nothing is exact. But you have to have a way to say, if I'm too far less than 64, I've cheated my consumer. If I'm too over 64, then they're getting something that they didn't pay for. And as a producer, I don't want that. So now, I have to check these. I randomly sample 40 containers. This is my N. The mean stays the same. Oh, sorry. Nope, they have a mean of 64.05. This is the mean for the sample. Your mean for your population stays the same. Your standard deviation is going to change. So you take their sample mean minus your population mean, and you get a z-score of 2.94. That's pretty high, isn't it? Don't we consider plus or minus 2 to be unusual, plus or minus 3 to be very unusual? Then I would say this is an unusually high container. And I would say, yep, you need to reset this. Because if I'm going to keep giving everybody extra, I'm going to lose money. They're getting a little extra, but I'm losing money. Now, was on the other side of it, I'm not losing money. They're losing, the consumer's losing money. If I'm an honest businessman, I would still reset my machine, right? Because now my consumer's not getting what they need. If I'm a dishonest businessman, I would say I don't care about the left side, I only care about the right side. But this is one of the reasons why we test these all the time. To see where if it comes within reason. Okay, the last one. The lengths of lumber of a machine are normally distributed, so we're good to go from here. With the mean, and this is a population, with a mean of 96 inches and a standard deviation of 0.5. Look how small that standard deviation is. Because if you think about it, if you're building a house or you're building something, should your lumber be that far off? You don't want your lumber to be far. If you're looking for a certain length to be cut, and it depends on you making your house sound and stable and something that I don't have to measure and cut, you expect those boards to be cut correctly. So now you take a sample and you say, what is the probability that a randomly selected, oops, so this is from the population, that a randomly selected board, this is from your population. I have no N. Can't be a sample. Has a length greater than 96.25 inches, so I look at my curve, 96.25. Yeah, well, it's still less than 50% because I want it greater than. And look, I come out less than 50%. I'm in my ballpark. Then I do the same as the one before, where you compared your population to the sample. They just gave you an A, B, and C. Now, you randomly select a sample of 40 boards. What is the probability that their sample mean, is greater than 96.25? Same setup, except for you just have to change your population standard deviation divided by N, and use your new standard deviation. So now, look at my z-score. My z-score has increased. So it's over here somewhere, 3.16. There's a little wiggle over here. If I look to the right of that, it's a very, very small probability. Remember, most of my area is going to sit to the left of this guy. The sample is unusual to be greater than 96.25, while with the for the population, we say plus or minus 1 is where most of your data sits, 68% of your data. So that's fine. Up to 2 and -2, it is good. Whew. It was a long one.